In the vast expanse of space, a mysterious and invisible force dominates the universe. It's something we can't see, can't touch, yet it holds the cosmos together. This is dark matter. For centuries we've gazed at the stars, believing that what we saw was all there was, but the universe harbors a profound secret, a hidden reality that challenges our understanding of the cosmos. Our journey into the invisible universe begins right now. Our story begins in the 1930s with astronomer Fritz Zwicky. He was studying the Coma Cluster, a massive gathering of galaxies. Zwicky noticed the galaxies were moving too fast. The visible matter couldn't account for the gravitational force needed. It was as if an unseen hand was orchestrating their cosmic dance. Zwicky proposed there must be some invisible form of matter. He called it dunkel materie, dark matter. Over the decades, more evidence emerged, pointing to the existence of this mysterious substance. What makes dark matter so elusive is its very nature. Unlike stars or planets, dark matter doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes. But just because we can't see it doesn't mean it's not there. Imagine a bowling ball hidden beneath a stretched blanket. You can't see the bowling ball, but you can see the indentation it makes in the fabric. Similarly, dark matter reveals itself through its gravitational influence on the visible universe. The familiar matter that makes up our world accounts for just 15% of the universe's total mass. The remaining 85%, that's dark matter. This realization has profound implications for our understanding of the universe. It means that the cosmos is dominated by a substance we know almost nothing about. The universe is far more vast, mysterious, and awe-inspiring than we ever imagined. One of the most compelling pieces of evidence for dark matter comes from the Bullet Cluster. This collision of two galaxy clusters provides a glimpse into the unseen realm of dark matter. The collision separated the visible matter from the dark matter. Dark matter passes right through normal matter. Scientists mapped the mass distribution and found the strongest gravitational pull where dark matter was predicted. It confirmed an invisible hand shaping the cosmic landscape. Let's rewind to the early universe, just after the Big Bang. Dark matter played a crucial role in galaxy formation. The early universe was incredibly smooth, almost uniform in its matter distribution. Dark matter clumped together, forming vast halos of invisible matter. These halos drew in normal matter, forming stars and galaxies. Without dark matter, galaxies like our Milky Way might never have formed. Imagine our galaxy, the Milky Way, a majestic spiral of stars, gas, and dust. Encasing our galaxy is a halo of dark matter, an invisible spherical cloud that dwarfs the visible galaxy. These dark matter halos are a defining feature of galaxies throughout the universe. They're the invisible giants holding galaxies together and shaping their destinies. What is dark matter made of? That's the billion-dollar question. We know it's out there, we see its gravitational effects, but we haven't been able to directly detect the particles. Scientists have proposed many hypothetical particles as dark matter candidates. One leading contender is the WIMP, or weakly interacting massive particle. The search for dark matter particles is one of the most exciting frontiers in modern physics. Let's journey back to the first moments after the Big Bang. Dark matter played a crucial role in shaping the universe. It doesn't interact with light, so it wasn't affected by early radiation. This gave dark matter a head start in the cosmic race. It began to clump together under its own gravity. These clumps attracted normal matter, forming the first stars and galaxies. Imagine a distant galaxy, its light traveling across billions of light years to reach our telescopes. Along the way, it encounters a massive object like a cluster of galaxies. Massive objects warp the fabric of space-time. This warping bends the path of light. The light appears distorted, stretched, or magnified. This is gravitational lensing. We can map dark matter by observing this effect. Let's zoom out to the largest scales of the universe, where galaxies are interconnected nodes in a vast cosmic web. This web is a network of filaments and voids stretching across billions of light years. Dark matter shapes this cosmic web. These filaments channel the flow of matter and shape galaxy distribution. For decades, the identity of dark matter has been debated. Two main contenders emerged: machos and WIMPs. Machos are objects like black holes, neutron stars, and brown dwarfs. WIMPs are hypothetical particles interacting through the weak force and gravity. WIMPs became the favored candidate for many researchers. Machos likely exist, but aren't abundant enough to account for all dark matter. Black holes have a fascinating relationship with dark matter. While dark matter doesn't interact with light, it's still affected by gravity. This means dark matter can be captured by black holes, spiraling inward to eventually cross the event horizon. As dark matter falls into a black hole, it can form an accretion disk, emitting intense radiation. Studying this interaction could provide valuable insights into the properties of both dark matter and black holes. One of the most compelling pieces of evidence for dark matter comes from the rotation curves of galaxies. Rotation curves plot the orbital speeds of stars and gas as a function of their distance from the galactic center. According to Newtonian gravity, stars farther from the center should orbit more slowly. However, astronomers found that stars at the edges of galaxies were orbiting much faster than expected. This discrepancy provided strong evidence for the existence of dark matter. Despite decades of research, direct detection of dark matter particles has remained elusive. Scientists have built underground laboratories to search for the faint signals that dark matter particles might produce. These detectors are incredibly sensitive, capable of detecting the tiniest interactions. Yet so far, no conclusive signal has been found. The search for dark matter particles is a needle in a haystack problem. However, the lack of direct detection hasn't deterred scientists. It has spurred them to develop even more innovative detection methods. While dark matter is the leading explanation for gravitational anomalies, some scientists propose alternatives. One such theory is modified Newtonian dynamics, or MOND. MOND suggests Newton's laws break down at large distances or weak accelerations. MOND explains galaxy rotation curves without dark matter, but it struggles with galaxy clusters and cosmic microwave background. Some theoretical models predict that dark matter particles might annihilate when they collide, releasing a burst of energy. This annihilation process could produce observable signals, such as gamma rays or neutrinos. Scientists are searching for these annihilation signals, using a variety of telescopes and detectors. While no conclusive evidence for dark matter annihilation has been found yet, the search continues. Detecting these signals would provide smoking gun evidence for the existence of dark matter. Axions are another hypothetical particle that has emerged as a promising dark matter candidate. Axions are thought to be extremely light, electrically neutral particles that interact very weakly with normal matter. Scientists have developed ingenious experiments to search for axions. One such experiment uses a strong magnetic field to convert axions into detectable photons. The search for axions is a challenging but potentially rewarding endeavor. Dwarf galaxies are small, faint galaxies that contain far fewer stars than their larger counterparts. However, what they lack in size, they make up for in dark matter content. Because dwarf galaxies have relatively low amounts of visible matter, their dynamics are dominated by dark matter. This makes them ideal laboratories for studying the properties of dark matter. Astronomers are studying the rotation curves and stellar velocities of dwarf galaxies to learn more about dark matter. The cosmic dawn, when the first stars and galaxies ignited, was pivotal in the universe's history. Dark matter played a crucial role. Dark matter halos provided the gravitational wells for the first stars. These stars ended the cosmic dark ages with their light. The quest to understand dark matter is far from over. Scientists are developing new technologies and planning ambitious experiments. New dark matter detectors use cutting-edge technologies to improve sensitivity. Space-based telescopes like the James Webb will provide unprecedented views. The hunt for dark matter unites scientists globally. The answers could revolutionize our understanding of the cosmos. Dark matter is the invisible architect of the cosmos, shaping galaxies and stars. Yet, it remains one of the most profound mysteries. The quest to understand it continues, promising to transform our understanding of the universe.